let's explore a bit deeper into the limit of quotients. Take a look at this example. The limit, as x approaches 2, of the rational function square root of 3x plus 1 divided by x plus 2. Now remember that we always try direct substitution first. Let's make that note again. Always try substitution first. If it works, we're done. And that is super important. If it's a quotient, if our function is a quotient, we've got to look at the denominator and make sure it does not equal 0 when we substitute. And 2 plus 2 will not equal 0, so we are safe to proceed with direct substitution. Substituting that 2 into the places where x is will yield the following. Square root of 3 times 2 plus 1 over 2 plus 2. That is an answer, but of course we can simplify. Clean it up a bit. This becomes the square root of 6 plus 1 is 7 over 4. Also a fine answer. Notice that I'm avoiding using equal sign as long as I'm spacing my work far enough apart. Let's take a look at this example. Another quotient, the limit as x approaches 1 of the rational function x squared plus 5x minus 6 over x squared minus 1. Now we always try direct substitution first, and if it's a quotient, we always start with the denominator. If I substitute 1, 1 squared minus 1 equals 0. I cannot have 0 in the denominator. I cannot divide by 0. So I need to think of a way to work with this function so that it will look different. Now I notice these are two quadratics, and I can think maybe I can factor. Factor is a strategy that we often are able to use to manipulate our function to look differently so that we don't get 0 in the denominator. Let's try it. I'm going to rewrite this limit as x approaches 1. My denominator is easy to factor. That's x minus 1 times x plus 1. In the numerator, I notice negative 6 is the constant, so I think to myself what multiplies to make negative 6 but adds up to positive 5, and I've got it. The factors are x minus 1 and x plus 6, because 6 times negative 1 is negative 6, and 6 minus 1 is 5. Now with what I have here, I am able to divide out the common factor x minus 1. Now I notice that my denominator will no longer be 0 because 1 plus 1 is 2. Now I proceed with direct substitution, and I can do 1 plus 6 over 1 plus 1, and that makes 7 halves. And I have a limit. The limit as x approaches 0 of the rational function square root of x plus 9 minus 3 divided by x. Now I notice right away that because x is approaching 0, direct substitution will yield 0 in the denominator. So I know that I cannot just plug 0 in and be done. Now it doesn't look like I'm able to factor this, so I have to think of another strategy. And a good strategy for when I have radicals in the function is to rationalize. That's what we're going to try here. Rationalize. Let's make that note that if we rationalize, it can often help us have a function that's written in a different way that won't yield 0 in the denominator. So that means we multiply by the conjugate. So we multiply the numerator by square root of x plus 9 plus 3. instead of minus 3. And because we did it in the numerator, we're going to do it in the denominator, meaning also multiply the denominator by square root of x plus 9 plus 3. So to rationalize means that we multiply numerator and denominator by the conjugate. Let's see how that helps us. I'm going to rewrite this limit expression, limit as x approaches 0. Square root of x plus 9 times square root of x plus 9 makes regular, so to speak, regular x plus 9. Multiplying square root of x plus 9 plus 3 and square root of x plus 9 minus 3 makes opposites that add up to 0. And then negative 3 times positive 3 makes negative 9. In the denominator, I have x times the quantity square root of x plus 9 plus 3. Let's see how I can clean up this expression. Positive 9 subtracts with negative 9, so I'm left with the limit as x approaches 0 of x over x times the quantity x plus 9 plus 3. And notice again, I can simplify by dividing out these x's. And notice that that x that first gave me 0 in the denominator has now been divided out. Yay! I will be able to do direct substitution next. Let's rewrite what we have first. The limit as x approaches 0 of 1 over square root of x plus 9 plus 3. And now I will use the direct substitution. Plugging in 0 to where x is, I will get 1 over square root of 0 plus 9 plus 3. Now this is an acceptable answer, but I'd like it to look a little bit neater, so I'm going to clean it up a bit. 0 plus 9 is 9, and the square root of 9 is 3. So 1 over 3 plus 3, which is also an acceptable answer, but still we can get a bit neater and write 1/6. Very good. In this next example, we're looking at average rates of change. Find the limit as x approaches 2 of the average rate of change of f of x equals x squared plus 3x from 2 to x. Now recall that the average rate of change of f from a to b, as long as a is not equal to b, is the change in y over the change in x, or f of b minus f of a over b minus a. Super important to remember the average rate of change. Let's set up what that would look like for our function. So for our function, the average rate of change, I'm just going to abbreviate here, will be f of x minus f of 2 over x minus 2. Now specifically for our function f of x, it will look like x squared plus 3x minus 2 squared plus 3 times 2 over x minus 2. Now if we clean this up a bit, we've got x squared plus 3x minus 4 plus 6 is 10 over x minus 2. Now we will apply the limit as x approaches 2. The limit as x approaches 2 of this rate of change that we just wrote, x squared plus 3x minus 10 over x minus 2. Now, noticing that we have a rational function, we check that the denominator won't be 0. But plugging in 2 into x does make the denominator 0. 2 minus 2 equals 0. So we have to figure out a way to rewrite this function. Remember when we factored? Usually, factoring is a good way to rewrite the function. So let's say this is equivalent to the limit as x approaches 2. The denominator, of course, is still x minus 2. And I've got the factors. X minus 2 times x plus 5. This way, x minus 2 factors out, and with what's left, I can substitute the 2 into the x. This will be 2 plus 5, or 7. And there I have it. Looking at one more, find the limit as h approaches 0 of the difference quotient of f of x equals x squared plus 3x. Same function that we did in the previous example, but now we're using the difference quotient, another very important one to know. The difference quotient of f at x, such that h will not equal 0, is f of x plus h minus f of x over h. Again, super important to know. We'll be using this a lot in calculus. Let's begin by writing our difference quotient for our function. So, plugging in x plus h into where x is looks like this. X plus h squared plus 3 times the quantity x plus h. That's this part of that difference quotient. Then I have minus f of x. So minus the function x squared plus 3x, and then that is all divided by h. And again, I can clean this up a bit. So at first we have x squared plus 2xh plus h squared plus, now we distribute 3 times x and 3 times h, 3x plus 3h, and then we distribute the negative to the x squared plus 3x, minus x squared minus 3x. And then, of course, all divided by h. Now notice what we can clean up is all the stuff that doesn't have h in it. This term x squared minus x squared. This term 3x minus 3x. And the only terms we have left have h in them. Let's rewrite what we have left. 2xh plus h squared plus 3h over h. And notice we can factor out an h. 2x plus h plus 3 over h. And now we can divide by the common factor h. With what we have left, let's go ahead and set up our limit. The limit as h approaches 0 is what we need to write. The limit as h approaches 0 of 2x plus h plus 3. Using our direct substitution, 0 into the h will look like this. 2x plus 0 plus 3, which, while it is a valid answer, can easily be simplified to 2x plus 3. And we're done. Notice how that limit of the difference quotient looks different than the limit of the average rate of change. Thanks for watching.